2, 1, start.
Hello everyone, welcome to the fourth HIWeather webinar toward improved hazard forecasting. My name is Jenny Zhang. I'm the lead of the task team to multi-skill hazard forecasting under HIWeather project. Today's program is hosted by Martin Wegman from WMO and will be facilitated by Paul Zhou. Paul is from the Environmental Canada of Climate Change. Although now he's retired, but he is still very active in committees and research. So I'm affiliated currently with the National Center for Atmospheric Research located in Boulder, USA. So without further ado, I'll now turn to Paul.
All right, thank you. We have an exciting 6 presentations here from all over the world. But first, I should say good day, good afternoon, and good evening. The first speaker up is Jenny, and she will provide an overview of the multi-scale hazard forecasting task team. Over to you, Jenny.
Okay, thank you, Paul. So in this first talk, I'll give an overview of the multi-scale hazard forecasting task team research and activities. I'll start with a brief overview of the HIWeather project. The HIWeather project is a 10-year WMO WRP research project established in 2015. The International Coordination Office is in CMA, Beijing, established in November 2018. Brian Golding from United Kingdom and David Johnston from New Zealand are the co-chairs of the project. There are 5 task teams focusing on 5 different themes of research. The overarching goal for the project is promote cooperative international research to achieve a dramatic increase in resilience to high-impact weather worldwide through improving forecasts for timescales from minutes to 2 weeks and enhancing their communication and utility in various applications. The scope of this HIWeather project is defined by these 5 hazards: urban flood, disruptive winter weather, wildfire, urban heat waves, and air pollution, and extreme local wind. As the cities are getting larger and larger, the challenge for accurately predicting hazards becomes greater. Partly because the mega cities, they are highly populated, so the hazards can cause tremendous danger and even loss of life to many people. So there are 5 research themes under the HIWeather project. They are organized through task teams. So each task team consists of a number of members. In the multi-scale hazard forecasting, we have currently 9 members from several countries and continents. If you are interested in becoming a member, you can contact me because we still need expertise, especially we need people in the area of coupled hazard modeling. The hazard forecasting involves several key processes, starting from multi-scale observations. These observations can be directly used to produce the hazard forecasting, or they can use the by numerical models through data simulation to produce NWP-based forecasting, weather forecasting, or they can be used in nowcasting systems to produce very short-term forecasting. These weather forecast output have to go through some intermediate processes, including user-oriented post-processing. This has to also provide uncertainty information, of course, and machine learning technology or a coupled modeling. Of course, the coupled modeling is most complex, and it's still mostly in the research stage. A lot of hazards occur in localized regions and in a very short time scales. Even for systems that are large scale in nature, like a hurricane or winter weather. So although we can issue advisories based on current numerical model results, we can tell people the potential areas, large areas, there will be a possibility of a hazard, but we still cannot do specifics of location and timing. So these are really challenging problems. So given the above background, our key research areas focus mostly on the high resolution observation and modeling, or nowcasting technology, including observing kilometer scale weather hazards and impacts, hazard nowcasting methods, coupled kilometer scale data simulation methods, kilometer scale hazard prediction with improved convective initiation, microphysics, land surface interactions, and PDL parameterizations. Coupled kilometer scale ensemble predictions, and advanced user-oriented post-processing products, including uncertainty. These two maps illustrate the current and future global observing systems. On the right, that's the future new observations. These different observations, they really represent different scale of atmospheric motion. So in order to assimilate these different types of observations, there are great challenges for data simulator and modeler. For example, because these observations have different spatial and temporal resolutions representing different scales of atmospheric motions, then the data simulation method has to be able to optimally assimilate different types of observations. But current data simulation system usually either focus on the large scale observations or convective scale observations. So we still have a lot of work to do to be able to assimilate all these multi-scale data observations and to do it optimally for all. Another challenge is with all this big vast amount of data, we need a better understanding and handling this data. And they all have different characteristics. This also poses another challenge. Of course, data pre-processing, quality control, error, quantification, these are all challenges for assimilating all these different types of, especially the new observations. The networks currently quite useful for kilometer scale data simulation include radar, surface station, geostationary satellite, lightning detection, profiler, UAV, smartphone, and etc. Okay, here is an example to illustrate the role of a high-resolution observation using lightning data observations. You can see what I show is one is observation on the upper left. On the upper right panel, it labeled RAD. That means that forecast use the radar observation only to produce the forecast. And the lower left shows the result by combining radar and the lightning observations. You can clearly see when we combine these two, we are able to successfully forecast the reinitiation in front of the old decaying system. So of course, the score is improved by combining these two types of observations. Okay. Nowcasting is very important for hazard prediction, but we still have a lot of research questions to be answered. For example, machine learning is a new technique that shows lots of potential. So on the right-hand side, there is a figure showing one result from a recent study by Han et al. It shows the machine learning technology is able to predict the storm initiation that wasn't exist at all half hour ago, but then 30 minutes later, using the machine learning method, we are able to forecast the initiation. But although there are some false alarms still. Okay, another I want to highlight is another question is the use of geostationary satellite data for nowcasting. This is especially important for regions without radar networks. Okay, next one. So for the coupled modeling, at least three, many questions, research areas, and 3 topics. The first one is, of course, we need still to improve the accuracy of weather models. In order to do that, there are several, at least 5 topics. I think these are all quite very important in order to improve the accuracy of weather models such that these forecasts are useful to drive the hazard modeling. And the second topic is to improve uncertainty prediction. For the high resolution kilometer scale modeling, one question often arises is how to make the perturbation. How can we consider large scale and convex scale perturbations? How can we get both optimally? For the coupled hazard modeling, of course, data archive distribution, this is quite a basic thing, but it's still lacking. Then pre-processing weather data and two-way coupling to model feedbacks, coupled data estimation, these are all important issues. On the right, I'm just showing an illustration that the model resolution really make a big difference. So on the lower right panel, it's a 500-meter model run. You can see this here. The hook echo is successfully forecasted, but at the 2 kilometer, you are not able to forecast the hook echo that caused tornado outbreak. Okay, this slide I list the recent activities by the team. The team worked on a BAMS review paper in the last 2 years entitled Multi-Scale Forecasting of High Impact Weather, Current Status and Future Challenges. This paper has recently been accepted. I think it will be in print pretty soon. So various members participated in international projects such as this project in various regions, some Asian, some in Europe. And of course, our members have a much wider research areas than I just highlighted. For example, they have people doing hurricane prediction, heat wave prediction. I don't have time to highlight their research, but in today's program, I hope you can get a flavor of these researches. There will be 3 high weather cross-cutting projects in the next few years. So our task team is actively involved in 2 of these 3 projects, end-to-end value chain evaluation project and toward the perfect warning book writing. So thank you for your attention. So now I can answer some questions.
All right. Thank you, Jenny. So I should have asked everybody to send their questions as they came into your head. But if anybody's got a question, please type it in the Q&A feature of Microsoft Teams. So let me ask the first question about urban.
Mm-hmm.
One of the issues of urban is air quality and heat. You know, in Europe, many people died in one of the heat waves in the big cities because of the extra heat. Is HIWeather focused on that at all?
Like one of our members is working on the heat wave prediction. He's from India. So because the heat wave is also a big issue for India. So myself is not expert at all in that area, but yeah, we do have some people working on that. I think really the main issue is still it's maybe not that hard to forecast the larger scale, you know, to give advisory of the heat wave in a large area. But the problem is when it's combined with the urban heat island, it may make it more difficult.
All right.
Mm.
Right. Okay. Do we have any questions from the other speakers for Jenny? Okay. Okay. Why don't we move ahead and invite Francois Boussier to speak on seamless ensemble nowcasting of thunderstorms and flash floods. Go ahead, Francois. And thank you for staying up so late.
Okay, yes. So thank you. This is François Boutier speaking from Toulouse.
I think you need to show your screen.
Yes. Can you see my presentation?
Not yet.
What about now?
Yes, we see it now. Very good.
Okay, thank you.
Just go to full screen.
Okay, so I am François Boutier. I'm a scientist working in Météo France. And I will discuss ensemble nowcasting of thunderstorms and flooding. So by seamlessness, we mean that we would like to extract information from a complex set of numerical predictions. So that's important for thunderstorms and flood hazards, because these phenomena have short time scales, and they may sometimes have very low predictability. That means they require very fresh forecasts, so frequently updated forecasts to issue the appropriate warnings. So there is a variety of prediction tools available. Actually, there are many of them, and for many users, there's too much information to take in. For instance, there are the observations, which can be used for nowcasting, either as persistence. Sometimes they can be extrapolated over short timescales. Then there are numerical nowcasting models, which are NWP models, so weather prediction models that are configured with very short cutoffs and rapid update cycles. So these can be combined with conventional numerical weather prediction and longer range forecasts. So usually the forecasts from NWP with longer cutoffs will have better quality, but they will be less timely, so they may or may not be useful for nowcasting. So to cope with this mass of information in real time, it is suggested here to treat all of them as a large ensemble, where the members, they are heterogeneous, they do not have the same quality, and then the ensemble size depends on the forecast horizon, as we will see in a minute. And then this ensemble has to be interpreted as probabilistic information and translated into terms and products that are simple enough for the users, in particular to hide the discontinuities and artifacts related to the heterogeneity between the models and biases and calibration issues. So we will discuss three kinds of themes, so to speak. So there are the discontinuities between the prediction models that we would like to blend. Then there's the gap between what's modeled in the ensemble prediction systems and the parameters for which you would like to issue probabilities. And then there's the translation of numerical weather prediction information into understandable user warnings. So regarding the time continuity of the forecast products, it is useful to visualize the diversity of forecast models in a typical production suite as a two-dimensional diagram, where in the horizontal you have the validity time of the weather products, and in the vertical you have the production time, so the time at which the models are computed. So the diagonal, the gray diagonal is the present, and to the right you have the future. So the navy arrows, short arrows, represent the nowcasting systems, which are frequently repeated and have very short forecast horizons. And then from time to time there will be a longer range forecasts, either deterministic or ensemble predictions, who will tend to start later in the past because they require longer time to prepare the initial condition and perform the computation, but they will reach further into the future. So when elaborating an end user forecast, we would like to combine all this information in a data window represented here in the dash gray. And in that window, we treat all the up-to-date forecasts as an ensemble. So some arrows are shorter than the others. That means that short time ranges, you will have more members than at longer time ranges. And that window is moving as time goes by, so that it's important to minimize the jumpiness in the forecast. So as new forecasts are introduced in the update of the forecasting products, we want to avoid discontinuities, and we want to avoid jumpy warnings. That is, we don't want to issue a warning that we'll have to cancel and reissue a few hours later. That's very inconvenient for many users. Another requirement of time continuity is that the forecast products should relax to the observations as the forecast horizon tends to 0. So then there's the discontinuity in parameter space between what is available in the models, including the nowcasting systems, and the parameters in terms of which we need to make warnings. Taking as an example the thunderstorms, well, there are many possible impacts that are possible from a thunderstorm cloud. Some are easy to observe and are relatively well modeled nowadays, like radar effectivities or satellite cloud tops. Others, like tornadoes or hail, are much more difficult to observe and to model. So the quality of the forecast will be a function of the quality of the clouds that are in the forecast models, but also our ability to diagnose user-oriented parameters from these model states. And that's an area of active research. Then there's an important issue for thunderstorms and heavy precipitation, that these parameters, these events tend to be relatively small and short-lived, and their forecast errors are of the same order of magnitude as the event itself. And that means that there will be what we call the double penalty. That is, that if you make a straight forecast product from interpretation of the forecast on the model grid, if the model has a high resolution, so if it simulates high resolution events, most of the forecasts will be wrong, as explained on the slide, because with even small displacement in place or time of the forecast events, you will have a majority of wrong forecasts, either false alarms or missed events. And that is very bad for the user experience. So the solution to this double penalty problem is to express the forecast in probabilistic terms. That means that instead of forecasting, in the example, a storm risk on point X only, you will forecast it with a limited trust on a wider area. That will increase the detection rate. And obviously, there's a compromise to be found between the detection rate and the number of false alarms, so that it has to be decided with respect to the kind of users and what the users require in terms of the number of false alarms. So to issue probability forecasts, the tool of choice is the ensemble prediction. So as you know, ensemble prediction is the process of running in parallel several numerical forecasts that are perturbed in such a way that they represent a sample of the possible future evolution of the atmosphere. And they can be used to quantify the probability of high impact weather events. So here is an example with a 12-member rain forecast, where there are a few members correctly predicted a high precipitation event. So if you have time, you can may look at each of the 12 members on the left, but we would like to summarize this information. So one way to summarize would be to convert at each point the forecast field of precipitation using, say, a quantile statistic. So if I extract the 85% percentile shown at the top right, we get a smooth field. But the big problem is that the maximum precipitation is removed, even with such a high percentile, because the event, the high impact event in this case, is intense, but it has a small scale and there are uncertainties on its location. So to avoid this dumping of the signal, it's necessary to do more clever processing of the ensemble output, typically neighborhood methods. And here in this an example on the bottom right, where we have applied a max neighborhood over a small radius, plus statistical calibration to remove ensemble biases, and that provides a summary of the ensemble prediction with the more or less correct amplitude and location of the hazardous area. So speaking of flood, So that there's a complicated relationship between precipitation forecast and flash floods. Precipitation is the main cause of flooding, but it has to be processed with care because instant precipitation rain rates are a poor predictor of flood risk. If you may have seen weather events where there's intense rain, but from moving clouds, so that there's no accumulation that's hazardous anywhere. On the other hand, you may have moderate precipitation with coming from clouds that move, but they tend to repeat themselves over the same places because of what we call convective regeneration, which is often linked to orography or convergence lines. So it's important to assess the flood risk in terms of rain accumulation using a model that's as physically realistic as possible, so that it should represent these processes. So speaking of AI, that means, I mean, these events are fairly intense and high impact, but they have a complex structure in space and time, and it's difficult to guess from examination of the rain field in real time whether we are having catastrophic accumulation or not. So conventional OPS extrapolation methods are difficult to use for this kind of systems because there's a complex relationship between the motion, the rain field, and the flood risk. So there are other problems linked to the hydrological aspect of the flood formation. In particular, the vulnerability of the populations to the flood is very dependent on the local history of extreme precipitation and floods. And so when issue the warning, it's important to pay attention to the climate of precipitation accumulation in a very detailed way to assess whether this is a normal event or whether this is an extreme that is hazardous. So in summary, these complexities mean that it's important to process precipitation forecasts not as a scalar field, like we have done for thunderstorms, but we need to pay attention to the space and time structure of the precipitation scenarios and extract the quantities that are really important for flood prediction. So here's an example of that. Precipitation forecast errors are usually heavily correlated in space and time. So for instance, if you take 2 quantiles of rain accumulated over 3 hours, so shown on the left, 2 plots, and you sum them, you will get a field that's very different from the 3-hour accumulation of rain. In other terms, the sum of rain quantiles is quite different from the quantile of the rain accumulation. So you cannot just issue short accumulations of rain, derive probabilities from that, and derive flood forecast from that, because the flood is sensitive to accumulation over several time scales. And if you neglect that, you will usually end up with very large errors in the prediction of rain accumulations. In this example, we have up to 30% error in the prediction of the high precipitation area. So we will finish by 2 examples of pre-operational products that use these ideas. So one about thunderstorm. So this is a forecast product, the short-range forecast product of thunderstorms that is a blend between 3 ensemble prediction systems that are very different from each other in terms of forecast ranges, physics, and resolutions. And an evaluation of this blend shows that it's much better than each of these systems taken in isolation, even after calibration. And so by blending, we mean that we have weighted each ensemble as a function of their average quality, and the ensemble members they are smoothed in space using a max neighborhood method, which has been tuned using a machine learning algorithm over a rather short training period to have the requested ratio between false alarms and non-detections. And that's important because it is related to the way users will perceive this product for their everyday activity. So it's a product for the wide public. As a byproduct from the machine learning, we can assess the effective predictability scale of thunderstorms, which in this case is of the order of 70 kilometers. So that's much lower than the resolution of the AROM system, which is the highest resolution model, which has a kilometric scale resolution. So that shows the predictability of the thunderstorms in current systems. And an example about prediction. So this is a nowcasting system that uses deterministically a blend between an optical flow extrapolation of sequences of radar images and short numerical forecasts from a kilometric scale model. So every 15 minutes we update this OPS model blend. So that's a deterministic rain prediction system. And we have demonstrated that the forecast quality is much improved when we use it in a probabilistic way. So we convert this deterministic system by building a per person lagged ensemble. So we use the three most recent members at any given time, and we apply a neighborhood processing to smooth out the small unpredictable details and optimize the forecast error statistics, so which are illustrated in the lower left diagram. So it's called a rock diagram, and it shows that we improve a lot the detection rates without creating too many false alarms by applying this neighborhood processing. So there are several ways of doing this kind of processing. One can process the rain field on short intervals as a scalar field, or we can use the scenario approach I outlined earlier by adding noise that's coherent in space and time to increase the ensemble size, because remember it is very small, and compute probabilities after that operation. So each of these two methods have their own benefits, and we are still working to determine what's the best solution. So as a conclusion, how can we improve the nowcasting of thunderstorms and flood along these lines? So there are two avenues. One is to improve the forecasting systems themselves. So there are ways to improve the observations and the models. Observations that are critical in many cases are low tropospheric observations, and the technologies exist, but the space-time coverage is essential for nowcasting. And regarding the models, so there are improvements that can be done in the model themselves and data assimilation, and there is potential from the artificial intelligence community, which should be combined with the numerical approaches. And on the other hand, there are ways to improve the use of the data that's already produced. So I've already described the ensemble processing methods that for which there is much to be improved. And it's important to realize that the probabilistic processing forecast output, it's sensitive to the users for which the products are meant. So that means more work to optimize the product for each of them. And I recommend using as much as possible several model systems because it's a consistent result that forecast products can be much improved thanks to the combination of independent prediction systems. And lastly, I often get the question, why don't you use AI methods for nowcasting? Well, there's a basic problem that these high impact thunderstorms and flooding in particular, they're still relatively rare events compared to their complexity. So it's still difficult to build the training samples to use sophisticated AI methods, but we will see in the future what they can do. That's the end of my talk.
All right.
Thank you. Have you got any question?
We're a little bit tight for time, but we'll. I think you had some questions on the chat, so you might want to respond to them afterwards. But there was one question that, and I think you addressed several of them. But the one question was, how do you foresee? This is from Beth Ebert. How do you foresee blending observational-based nowcasting systems that are probabilistic? And I think she's thinking about the steps algorithm for precipitation, and how do you combine it with the model ensembles? So how do you combine observational-based ensembles and model ensembles? How do you envision that?
Well, the proposal is to treat them as an ensemble, as I described in my talk. So the observation-based extrapolation can be regarded as one ensemble member, which is very short. And when you derive probability, you can combine the information from that system with a numerical prediction system. So you don't need to do interpolation of the fields themselves, but you use several members in your probability computation.
Right. So take a look at the question from Beth. It's because she sees it as different fields. Anyway, I think we have to move on, and we'll come back to you. There were several questions for you, so we might come back if there's time at the end.
Okay,
so
thank you.
We have, thank you very much. Now moving over to Tammy Weckworth. She's from the National Center for Atmospheric Research, and she's going to talk about new observations of water vapor. MicroPulse DIAL lidars. Okay, over to you, Tammy.
Hi, thank you. Can you hear me okay?
We can hear you. We don't see your screen at the moment.
Oh, that's...
Francois, you might have to unshare, maybe.
Are you seeing my screen yet?
Not yet.
How about now?
No. Not yet. Oh dear. Oh, I think something's happening.
Okay.
There we go. We see it.
All right. Very good. Thank you. Hello out there. Back to Boulder we go. So I'm excited to talk to you about new observations that we have of water vapor MPDs, which stand for MicroPulse Differential Absorption LiDARs, and their impact on convective weather forecasting in an OSSE, or Observing System Simulation Experiment. Thank you so much to the organizers for letting me talk about this exciting work that we're doing at NCAR. I have several co-authors on this presentation, and we're all at NCAR. These include Jun Kyung Kae, Scott Spuler, Glenn Romine, and Jenny Sun. So first I'm going to tell you about the instrument, and then I'll tell you about the OSSE. So MPD stands for MicroPulse DIAL, and this has been developed through a really fruitful collaboration with Professor Kevin Rapaski at Montana State University, as well as the engineers in the Earth Observing Laboratory at NCAR. So let me break it apart into the different acronyms that we put together to create the name of MPD. First of all, MP stands for micropulse, and this is a class of laser remote sensors that use low energy or micro pulses of light at 5 microjoules at high repetition rates of 7,000 hertz, and we use photon counting receivers. The D stands for dial. It's an embedded acronym in there. This is a class of laser remote sensors that measure the difference in absorption between 2 nearby frequencies. And I'll show you a little bit more about that in the next slide. And then the LiDAR is for light detection and ranging, which is a type of active remote sensing that's similar to radar, but instead uses light in the form of a pulsed laser to measure the ranges. So I'd like to describe how the dial technique works. It's really slick and clever, powerful technique that gives excellent data quality. So I'm going to show you the dial technique that we're using for water vapor, but it's very similar for ozone as well, in that they both use 2 tunable wavelengths or frequencies that are very close to each other. For our water vapor MPD, we're using 828 nanometers. So if you look on the figure on the left, we're showing that we're transmitting an online frequency that's very close to a water vapor absorption peak, around 828 nanometers. And then we transmit an offline signal that is not absorbed by water vapor in the atmosphere. And we simply look at the ratio of the signal returned between the online and offline transmitted frequencies, and that gives us the range resolved water vapor number density or absolute humidity. So the advantages of this technique are that it's a direct measurement. There's no external calibration required for the narrow bandwidth frequencies that we're using, and it provides very high accuracy. The challenges are that it gives or requires very high spectral purity and fidelity of the laser transmitter. We have to be able to tune it exactly, and we have to know where it's tuned exactly to be able to make these precise measurements. But we've achieved this with relatively low cost and eye safety and low maintenance using commercial off-the-shelf parts. Here's an example of data that we've obtained from MPD from 2 different field campaigns. The top 2 panels show data from a pecan field campaign in Kansas in 2015. The bottom 2 panels show data from Argentina from the Relámpago field campaign in 2018. So for the top panel of each of these, I'm showing the relative backscatter from the surface up to 12 kilometers above ground level. So there's just a time series of these profiles from MPD with 5-minute temporal resolution. The second panel for each of these cases, or each of these field campaigns, shows the water vapor. And you can see lots of variability in the magnitude of the moisture as well as the depth of the moisture that's returns. So we're seeing lots of diurnal variation in the depth of the water vapor because the background solar radiation is really hard to filter out during the daytime, so we can't see as high up during the day as we do at night. But given that, we also have some gaps in the data when there's strong clouds. We can't see through optically thick clouds with the LiDAR. But you can see that the systems were just operating continuously. We have over 95% uptime from these both of these field campaigns. We just set it up and we tune it to the appropriate frequency, and then it just operates continuously in an unattended mode. You can see lots of variability in the magnitude and the depth of the moisture, and we're really excited about this new capability. We also did some validation work of the MPD and compared it with more mature instruments that are capable of measuring water vapor profiles. So these instruments were all co-located with MPD during a couple of field campaigns. The top left panel shows comparisons with radiosondes, and we see a correlation coefficient of 0.95. We're really happy to see that high agreement. But the radiosondes are just launched a couple times a day. We don't have continuous comparisons. And the top right panel shows us continual comparisons with an ARI. That's a passive remote sensing instrument that operates continuously, just like MPD. And there we see the correlation coefficient of 0.79. The comparisons are also good with profiling microwave radiometer, and also good comparisons with integrated precipitable water from ground-based GPS receivers. The panels on the bottom right are particularly interesting. They show a 24-hour time series comparison of MPD on top, ARI in the middle, and profiling microwave radiometer on the bottom. So they all three compare very well in water vapor depth and water vapor amount and variability. However, MPD is the only one that shows elevated moist and dry layers. The passive remote sensor retrieval capabilities just don't allow us to retrieve the information that illustrates an increase in moisture with height. So the active remote sensing capability of MPD is much preferred when there's changes from the standard decrease of water vapor with height. So we're using MPD to evaluate the precursors to convection initiation and to better understand water vapor variability and vertical variability of moisture. We're also using MPD to study the observation impact of assimilating water vapor profiles into NWP models to improve the forecast skill of high impact weather events. So this is one of those efforts that we're working on right now using an OSSE. This OSSE effort is based on a squall line that occurred on the 15th of July in 2015 during the Pecan field campaign. You can see the 2-hour evolution of this system becoming more organized as the MCS propagates across northern Kansas. This describes the OSSE experimental design. So what we're doing is we start by running a 40-member WRF, Weather Research and Forecasting Ensemble, to find the member that best represents reality. And then we call that the nature run. And that's shown in the lower left, second from the bottom left. And so that becomes our truth in this OSSE study because it most closely compares with the real observations that are shown in the upper left thumbprint. The worst member that performs the poorest, we're calling the control run. And then we're going to use that to assimilate simulated data. We're going to put simulated data into the control run to see if it improves the forecast to determine if it becomes more similar to the truth or the nature run. So you can see that the control run is pretty poor result. It hardly produces any precipitation at all. So in addition to the subjective comparison of these thumbnails, we can also use objective measures to compare the intensity, shape, location, and evolution of convection with the real observations in defining the nature run and the control run. So this describes the model setup. In the upper left, you can see that we're using WRF with a 15-kilometer outer domain and 3-kilometer inner domain with 70 vertical levels. You can see the physics schemes that we're using, and then the time series, the timeline in the center shows how our assimilation goes. So for the nature run and the control run, there's no assimilation at all. And then what we're going to do is 2 different DA experiments, 2 different data assimilation experiments as described in the bottom left. We're going to do a sonde Q. That's what we're calling this DA experiment, where we use simulated data from Raywin sonde and assimilate that into the control run. So we're using Raywin sonde wind, temperature, and pressure, and Raywin sonde moisture as well. And we're going to compare that with an MPD-Q experiment where we take the wind, temperature, and pressure from the ray wind sonde, but instead of the water vapor from ray wind sonde, we're using water vapor from the MPD profiles. So we're doing the simulation of that for a 3-hour period, and then running the forecast to see how they compare. So here's the results of the forecasts. The top row shows the observations. The second row shows the nature run, which is our truth. And the third row shows the poorly performing control run that we're trying to improve upon with the data assimilation. The fourth row shows the results of the data assimilation experiment using only the ray wind sonde data. You can see improvement over the control run for sure. However, if you look at the bottom row, where the MPD-Q experiment using water vapor profiles from MPD, that produces the results that are most consistent with the nature run. The quantitative metrics also support this conclusion, which I'll show you one example of our quantitative metrics here. This is to compare the 1-hour accumulated precipitation fraction skill score. Here I'm showing the FSS for 2 different thresholds of 24 kilometers radius of influence for verification and a rain rate of 0.5 millimeters per hour on the left and 5 millimeters per hour on the right. So the higher the FSS, the better the forecast skill. It's clear that the control run in gray just does a very poor job of the forecast, just as we expected. The green line showing the ray wind sonde assimilated data does better, much better than the control run. However, the MPD-Q data assimilation experiment is better than all of the other forecasts. And this result also holds for nearly all rain rates, all radius of influences, and all forecast lead times. We looked at everything from 1 to 9 hours. So in summary, MPD is a tool we're really excited about. We can use it to accurately measure continuous profiles of water vapor. We currently have a network of 5 of them. Short-term forecasts of convection initiation, convective evolution, and precipitation of an MCS that occurred on the 15th of July in 2015 are improved by assimilating MPD profiling data in comparison to assimilating conventional surface and ray wind sonde observations. Assimilating MPD water vapor profiles increases the precipitation forecast skill over almost all forecast lead times and thresholds. And the improvement of the convective intensity and evolution forecasts we're attributing that to the correction of elevated moist air above or ahead of the MCS, which is possible due to our frequent updates of the MPD water vapor profiles with the high vertical resolution compared to ray wind sondes. And our ongoing work includes adding wind and temperature profiles into this OSSE study, and also we're looking into assimilating MPD using real data sets that we've obtained from recent field campaigns. Thank you very much, and I'd be happy to answer any questions that you have.
Thank you, Tammy. That's very interesting. We have a question from Robert Rogers. He said this is an interesting approach to the OSSE, picking the best and the worst ensemble members. The question is there a risk of identical twin issues if you're using the same basic model configuration for your nature run and for your DA run?
Yeah, that's interesting. I think this is a little bit different formulation of an OSSE than a lot of other people have used, although there is some there have been other researchers that have used the same way to create the nature run. So I think that what we're trying to do here is just to basically show the improvement to the forecast using various data sets. So by just looking at the difference within the same framework, I think it's a valid approach to assess which of these observational capabilities provides the best improvement to the forecast skill.
Right. I know we have 2 questions, one from Brian Golding and one anonymous, but for your runs, what was the did you have just one NPD, or did you have more than one? Did you have a network of these systems?
Yeah, sorry, I didn't point that out. I had a picture of the, okay, so we're using 11 MPDs right there located in the inner domain. So we chose the sites of the Radioson network in the central US and put the MPDs at the simulated MPDs at the same locations as those Radioson sites shown there.
Okay. So I'll ask one question. Your very last point and your conclusion, you mentioned using adding UV and temperature. What would you get? Where would you get that data from? What other sensors would you add to this list? To the MPD?
Right. So we're thinking that we want to use wind profiles from either radar wind profilers or Doppler lidars, and temperature profiles. We can obtain those from potentially airy systems. These passive remote sensors that give us retrievals of temperature and water vapor both.
All right.
So this is just in the OSSE framework. So we're just simulating these profiles and these capabilities using various data sets.
Right.
For number one, anyway.
Okay, that's great. It's one of those missing things that we've been looking for a long time.
Mm-hmm.
Water vapor. So thank you very much, Tammy.
Yeah, thank you.
Okay. So our next speaker is Nusrat Yusuf. She's from the National Severe Storms Lab, and she's the head of the Warn on Forecast program, and she's going to talk about data assimilation and high resolution modeling. So over to you, Nusrat. And we still got Tammy's presentation. You may have to unshare, and Nusrat, that's over to you. Nusrat, are you there? You may be on mute. Nusrat, we do not hear you.
Maybe we can go to the next speaker in the meantime, if that's okay.
Okay. Glenn, are you ready to go?
Yes, just a second here.
Okay, so we'll skip Nusrat and come back to her. Now we have Glenn Romine from the National Center for Atmospheric Research, and he's going to talk about convective scale hazard prediction and predictability. So we see your screen, you're good to go.
Okay, great, thanks, Paul. So, hi, my name's Glenn Romine from the National Center for Atmospheric Research. So I guess hitting you again from that community.
Can you hear?
Hello? Okay, I think that was Nusrat coming back. Do you guys want me to continue, or do you want to have Nusrat go ahead and go?
Glenn, you can go ahead.
Okay, thanks. So today I'm going to be talking about predictability and prediction of high impact weather. And just to make sure that we're kind of clear on definitions here. So the difference between predictability and prediction is really we can make a prediction. So basically we can simulate a weather event, and the extent to which that prediction is skillful, then that prediction has some aspect of predictability. And when we think of predictability, we can kind of break it down into two components. So the first component of that is known as intrinsic predictability. And in that sense, what we're really looking at is the extent to which tiny errors in the initial conditions of a forecast will grow during the forecast integration and lead to divergence in the forecast solutions. And so these are primarily driven by moist processes within the model, and that error growth is essentially unavoidable within a modeling system. So no matter what we do, there are certain processes and aspects of a prediction that we simply will never be able to accurately predict because it lies within this intrinsic predictability threshold. What is more commonly encountered in actual prediction is what's known as practical predictability. And practical predictability arises because we don't have perfect representations of the true atmosphere because we have an imperfect modeling system and errors in observing and weaknesses in our data assimilation methods. And when you combine all those together, it limits our predictive capability. That said, as we get better at all of these aspects, we can move closer and closer towards this intrinsic predictability limit, although we can never do better than that limit. So again, the limitations here come from imperfect observations, and this is simply because we don't have observations everywhere. There are spatial gaps, temporal gaps. Often measurements such as from radars and satellites are not of things that are atmospheric state variables. And in that sense, those observations are difficult to initialize models with. And our models are at best a simplified representation of the true processes within the atmosphere. And those errors we can always try to make them smaller, but to some extent they're difficult to get rid of entirely. And then when we talk about how we initialize our model forecast, well, we're conflating these two imperfect observations and modeling systems together using simplified methods, and collectively these all lead to errors that is what many of us are doing research on to try to minimize. So if we think about predictability of high impact weather, really a lot of where we have skillful prediction comes from the large scales, particularly during the cool season, because the energy basically from the large scales progresses downscale towards the mesoscale and the convective scale, and the convective scale is largely slave to the mesoscale environment that it lies within. And so if you could make a skillful prediction of the mesoscale, then oftentimes the sort of convective scale predictability aspects just sort of come along for free, which is great. And so in that sense, we can often make fairly skillful predictions of high impact weather even days in advance because of this relationship. So if we use higher resolution prediction models, we could start to make explicit predictions all the way down to the scales of individual thunderstorms. And we can even start to resolve some of the feedback mechanisms where error growth associated with that intrinsic predictability limit starts to push back upscale to where moist processes lead to changes in the mesoscale and synoptic scale forcing that provides that predictability. So let's look at a practical example of what this looks like when we have strong background synoptic forcing. So in this case, we're looking at a simulation of a convective event with 4-kilometer horizontal grid spacing. And so you can see there's a pretty well organized line of convection here. And it's a little bit, I guess you could say, mushy looking. But this comes from the fact that 4-kilometer grid spacing is kind of on the borderline of what's acceptable for high resolution explicit prediction. So if we go down to 2-kilometer grid spacing, you could definitely see more finer scale features, but in terms of the overall system placement and characteristics, very little difference from 4 to 2. And then we can do the eye test and go down to 1-kilometer grid spacing. And again, we see added detail in the 1-kilometer grid spacing forecast, but largely all the features are still in roughly the same place. We haven't really added a lot of new information by going to higher resolution forecasts. And so in this case, a lot of our predictive capability is really coming from synoptic scale forcing, and there's very little opportunity for error growth to go from the convective scale back up to large scales and to perturb this sort of large scale predictability of the system. So this is a wintertime system with strong forcing. Let's consider a summertime high impact weather event where we have weak background forcing. So in this case, we're going to use 3 kilometer grid spacing in this initial eye test. And so you can see there's a large convective system that's kind of in the center of the screen, and then there's another large convective system approaching from the northwest in the upper left corner. And so this is the simulation with 3 kilometer grid spacing, and now let's go to 1 kilometer grid spacing. Now you can see that there's quite a bit of difference in this trailing convective system, so the one that's back off to the northwest, whereas the more southern system really doesn't change position a whole lot. It's largely in the same. So this is a good example of where there's this convective feedback from the original system that's then affecting strongly the predictability of this trailing system. In this case, it's sensitive to a change in grid spacing. Now, it turns out neither of these forecasts is particularly great. So despite the agreement of the leading convective system, it's actually displaced quite a bit to the west of where the observed system is, which is shown in the lower right. Also, there's definitely some issues with the convective mode forecast back over the system that's, again, to the northwest. So largely, we see this if we look at climatologies of the predictability of precipitation systems from ensemble forecast systems with explicitly resolved precipitation. Here, these are fraction skill score, so higher values are better. And then the different colored lines here are time series of forecast skill for different rain rate thresholds, going from relatively light rain to heavier rain as we go from left to right. And so you can see that our most skillful forecasts are made during the cool seasons, so autumn and winter, whereas as we go into spring and then especially into summer, that our forecast skill tends to drop off. And this largely comes from that lack of strong synoptic scale background forcing to help provide the convective environment and the initiation drivers for where convection will form. And so I'd also like to make a pitch here for the value of why we want ensemble simulations for these types of prediction problems. So this is a somewhat messy plot, but try to work with me here. So in this case, we have ensemble sensitivity analyses shown in the color fills, and the feature to watch for will be these little red blobs. So in this particular case, we have an uncertain forecast of high impact weather in northeastern Texas Panhandle shown within that purple circle. And now, if we look at this initial condition, which is the upper left panel, we don't really see any bright red blobs, which would tell us that there's a strong sensitivity to this forecast event occurring in our initial state of the forecast system. Yet, if we look 6 hours in advance, we can see that there's now a little red patch that's appeared. And this is because some members in our ensemble system have developed storms in this area. And when these storms form, it produces enhanced moisture in the mid to upper troposphere from that convective activity. And that moisture pool is basically going to move downstream as the forecast progresses and end up over the top of our region of forecast interest over Northeast Texas Panhandle. And this is the type of flow dependent conditional predictability that we're really looking to get out of our ensemble prediction systems. And so another benefit when we talk about these high resolution ensemble forecast systems is that we really want to be able to get what are known as storm surrogates. So we're explicitly resolving individual thunderstorms at 3 kilometer and finer grid spacing. And we can extract information from those thunderstorms such as the strength of the updraft characteristics. So in particular, we know that thunderstorms that rotate in the middle parts of those storm systems are much more likely to result in severe weather occurring. So high winds, flash floods, tornadoes, and hail. And so we want to take advantage of that predictive capability from these storm surrogates. And instead of basically making forecasts of individual storms, we're going to make forecasts of hazards. And so we can basically stuff this calculation into our modeling system and output it at every time step so that we can capture all the information of the storm evolution within our forecast systems. And then we can take these storm surrogate fields and basically compute probabilities of hazardous weather occurring. And so in this case, in the upper left panel, these are places in our storm simulation where we have severe storm surrogates occurring, and we can smooth those out using a Gaussian smoother in the upper right panel. And then we can combine that with ensemble probabilities in the lower left to come up with a smooth ensemble storm scale probability field in the lower right. And if we do so, again, we're using fraction skill score, so larger values are better. We can see that those ensemble predictions of storm surrogates have substantial value in terms of providing enhanced predictive skill. So, and as we go to larger neighborhoods, we can see that that skill improves, but then we lose precision in terms of where severe storms are likely to occur in a given forecast. So those surrogates work pretty well in storm environments that the model knows how to do well, and those are storm environments that have relatively large convective instability. As we get into wintertime events that have generally lower convective instability, those storm surrogates tend not to do as well because the updraft speeds tend to be a lot smaller, and we don't see that strong updraft helicity signal. And so this is an example from a winter storm. So the observed reflectivity is on the left, and a simulation of that event is on the right. And if we look at storm surrogate forecasts for this event, we can see in those number grids there, pretty small numbers from storm surrogates, and it's offset pretty far from the storm reports that are shown in those circles. The small neighborhood is on the left, and then a larger neighborhood is on the right. So if we smooth things out a little bit, it makes things a little better, but it's still not a very good forecast. So this is a place where machine learning is really proving particularly valuable. So if we apply machine learning to the same forecast system, and instead of relying solely on storm surrogates, you can use environmental information from the forecast. That adds considerable predictive skill. In fact, if you look at the difference in predictive skill when we add a neural network versus using just severe storm surrogates, so again, higher values or more skillful forecasts, you can see that neural networks can add considerable value to forecast skill throughout the length of the forecast period. So, so that's pretty encouraging in terms of getting greater usability out of our existing forecast. So if we now try to look at what we can do if we go to shorter timescale predictability. So this is an example where we're looking at predictive skill when we use an hourly updating ensemble data assimilation system and prediction capability. So again, higher values are better. And so the predictive skill shown by the blue lines is from a mesoscale analysis system, so 15-kilometer analysis, and then making forecasts from that. And then the red and black lines show when we go to a 3-kilometer ensemble analysis and then make subsequent forecasts. And then we're looking at higher rainfall thresholds as we go from left to right. So for convective precipitation predictability, we can see added value from using a higher resolution analysis out to about 12 hours into the forecast, which is pretty encouraging. But so now let's see if we can go down to even finer scales. And I think this is the sort of area that Nusrat will be talking about. So now we're looking at 15-minute updates in a ensemble analysis system and then trying to make forecasts. So again, higher values are better. And these are subsequent forecasts that are made every hour over time. And what you can see in these is that the forecast skill starts off pretty good in these forecasts, but then diminishes, and by an hour later, they're not quite as useful anymore, and they sort of plateau and no longer sort of, you see that sharp drop off in forecast skill. So it kind of falls back to this mesoscale predictability of the background environment, and then the convective scale information from rapid cycling tends to trail off during the first hour of the forecast. We could also see that for dynamic predictions of storm surrogate objects that there's sort of similar behavior. There's sort of a rapid decline, and then it sort of flat lines out. And so there's this sort of background predictability, and then what can be added by storm scale predictability that's somewhat short. This is particularly evident if we go to very high resolution and not particularly well organized systems. So this is an example from a group in Japan that went to very high resolution. And so their highest resolution analysis is at 100 meters, which is third from the left. And so very high resolution analysis, very detailed. If you compare that to the observations that are on the far right, you can see this is a very accurate initial analysis relative to what's going on in observations. So, and if we look in observation space of this, we can see very small errors in the red trace, which is associated with that 100 meter analysis. These look really encouraging that they're able to add a great deal of value in the analysis. But what happens when we go to the forecast and boom, the whole thing kind of doesn't hold together very well. You see very rapid rise in error growth shown by the rapid increase in values in root mean squared error. And so this is somewhat discouraging in terms of our ability to add predictive value, even with the most sophisticated methods that we currently have available to us today. So this is a little bit sobering in terms of how far we still have to go in terms of being able to do this type of stuff better. So in summary, we could definitely get high predictive value on the mesoscale with current predictive capabilities. When we get down to the storm scale predictability, there's still a lot of challenges that remain. We're pushing up against the limits of intrinsic predictability, particularly when we're dealing with weak forcing environments where storms are not particularly well organized. And this is definitely a real challenge and will continue to be a challenge for the foreseeable future. And with that, if there's time, I'll take some questions.
Sorry. Thank you very much, Glenn. It was on mute. Sorry. In the interest of time, I'm going to shift towards Nusrat, and if there are questions for Glenn, please make them. We'll take them both at the same time with Nusrat's presentation, because she's her presentation is also on a really relevant topic here. So over to you, Nusrat. You're I can see your face, and so I'll turn it over to you. And Glenn, you might have to go unshare your screen or something like that. Over to you, Nusrat.
Can you hear me?
Yes, we can hear you. We see you. We just you have to show your screen now.
Okay. Can you see my screen?
Not yet, but give it a second or so. Not yet.
Okay, so I have to
Share desktop.
Share desktop. Okay. Okay, now you can see me, right?
I think it's coming. There we go. We see it. Just go to full screen. Yeah, we see you now.
Okay,
go ahead.
Thank you. Thank you. So I just want to correct, I'm not the lead of one-on forecast. I'm one of the developer of the one-on forecast system. So I'm a research scientist, and I am one of the developer of NOAA's National Severe Storms Laboratory Storm Scale and Sample Data Assimilation and Prediction System, which is known as the one-on forecast system. So basically there is a background here. So currently the National Weather Service warning process are largely based on warn on detection approach. So warnings are not usually issued for local severe weather until they see an early signal on radar or on the weather hazard is spotted. Now the warning is also issued on a very large area, so where everyone in the area gets the same message. So with the one-on forecast research and development project, we are aiming to use advanced data assimilation techniques and high resolution NWP modeling to accurately predict the storm scale phenomena. Now, if one-on forecast is successful, the forecasters at the National Weather Service will be able to provide more reliable guidance earlier than the current one-on detection approach, and also the hone in the area where the threat is the greatest. So, so why storm scale data assimilation and modeling? To predict individual convective storms and hazards associated with it, a storm and storm environment must be properly initialized in the NWP model. And that's why high resolution storm scale data assimilation in modeling is critical for predicting hazards. Now, we all know radar is the key observing instrument that observes the storm. Radar observes reflectivity, radial velocity, and dual pole observations with a high spatial and temporal frequency. But the radar, they do not see the true temperature, humidity, and the wind structure of the atmosphere. So as you can see here, these are the main prognostic variables in the model. So for storm scale data assimilation, most of these variables are unobserved, and you basically retrieve those observations from the radar reflectivity and radial velocity. And so basically the storm scale data assimilation is a retrieval problem. Now, the key difference between the current operational convection learning ensembles and the storm scale ensemble, like the one on forecast system, is lies in the temporal and spatial scales. So basically, the convection learning ensembles are typically designed for regional storm attributes, like, for example, where and when will the storm start or end? What storm types, what are the general hail, wind, rain, tornado risks, how widespread, questions like that. So basically, convection allowing ensembles aid in issuing watches and day one convective outlooks in the 6 to 36 hour time frame. Now, for the storm scale ensemble, on the other hand, can provide guidance of hazards associated with individual storm attributes with very high spatial and temporal specificity. So there are several data assimilation techniques that are used for storm scale modeling. For example, the variational techniques like the 3D VAR and the 4D VAR, and ensemble data assimilation approaches like the ensemble Kalman filter, and also the hybrid of these two methods. Now, the ensemble Kalman filter data assimilation approach is particularly useful because it naturally provides an ensemble. And as we all know, ensemble modeling approach, it is essential for probabilistic guidance. So, as I mentioned earlier, NOAA National Severe Storms Laboratory is developing a frequently cycled, frequently assimilated regional storm scale ensemble data assimilation and prediction system. So the goal is to provide a probabilistic model guidance for individual thunderstorm hazards like tornadoes, flash flood, heavy rainfall, high winds, damaging hail, etc. It is an on-demand system, so the placement of the domain depends on where the severe weather is anticipated, and it is guided by the day one outlook from the national forecast centers. So the goal, the overarching goal, is to support NOAA's watch to warning operations for hazardous weather threats. So once this system is transitioned to operation, the one on forecast guidance will be used by the national centers, local forecast offices, and other stakeholders. So this is the current configuration that runs at 3 kilometer horizontal grid spacing. So we have a 36-member ensemble, and it is a multi-physics ensemble with diversity in PBL and radiation schemes. And for the microphysics, we are using a sophisticated NSSL 2-moment microphysics scheme. And we assimilate reflectivity, Doppler velocity from WSR-80D radar. And we also assimilate geostationary satellite observations and National Weather Service operational conventional observations like the METER, marine radio sound, and others. Now, the fundamental concept is that if we can frequently assimilate radar, satellite, and routinely available conventional observations, and we initialize the individual storms and surrounding environment reasonably well, we should be able to predict its life cycle and associated hazards. So again, here you see the schematic on the right of the one on forecast runtime experiment. So once it is initialized, the system is cycled every 15 minutes, and 6-hour ensemble forecasts are launched on the top of the hour or every half an hour. Now, the one on forecast, the concept of one on forecast is conceptually very simple, but scientifically it's very challenging because it is the one-on forecast system. It is a next hour forecast problem, so it pushes the limit of not only the NWP modeling and data assimilation techniques, but it also pushes the limit of high performance computing. So now some example forecast from prediction from this one system. So this is the 19 July 2019 severe thunderstorm events across Minnesota and Wisconsin. On the left, you see the reflectivity and azimuthal wind shear in the animation. So there was up to a 3-inch size hail was reported across central and east central Minnesota, and wind gusts in excess of 80 miles per hour were reported across west central Wisconsin. And there was widespread and extensive tree damage and injuries, and many people were without power during that event. So on that system, we were live. We did run our system in real time. So what you see here are the paintball plots. So each color on the left, each on the right, each color represents a different ensemble member. So you see the left panel, it's a 6-hour forecast reflectivity paintball exceeding 45 dBz, and the gray shades that are overlaid at the observed reflectivity. So you see and the right panel shows the wind gas forecast exceeds 50 knot. So underneath the paintballs, you also see the local storm reports that appear. So as you can see, the model correctly predicted the upscale development and the southeast track of the storms in the MCS. And in the right panel, paintballs start appearing when the wind reports start showing up. So the transition to a damaging wind threats are captured reasonably well. And of course, it's not a perfect forecast, but it is capturing the revolution and the timing, which is encouraging. Now, this is a flash flood event from 2018. On the right, you see several flash flood reports in southwest Oklahoma City on 2nd May. And on the left is the 98th percentile accumulated rainfall from one-on forecast. So you can use that as the 98th percentile as a reasonable maxima of the intensity of rainfall. So what you see is that the northwest orientation of the MCS was predicted well on the Oklahoma County, and the storm trained over Oklahoma for more than 1.5 hours. And as you can see, the most intense rainfall actually correlates with the flash flood location. This is what we consider a pretty good forecast, not perfect, but something we hope is valuable. And of course, we don't do this well all the time, but just wanted to point out what the system is capable of. And the most encouraging thing is that on that day, the National Norman Forecast Office, the WFO in Norman, was looking at the one-on forecast for their guidance. And what was encouraging to see is that the Norman Forecast Office issued a flash flood advisory and later flash flood warning using the one-on forecast rainfall guidance. Now, we are expanding our application. We are also evaluating application of one-on forecast for hazards associated with landfalling tropical cyclone. So this is the one-on forecast rainfall guidance from Hurricane Harvey after the Hurricane Harvey made landfall. So as we all know, the Harvey dropped historic amount of rainfall and caused catastrophic flooding in Greater Houston region with more than 68 deaths in Houston. So from the left to the right, you see the rainfall thresholds. They are increased from 0.5 inches to 2 inches, and the observed rainfall is overlaid in the thick black contour. And also, if I don't know if you can see it, there are some green dots, which are the flash flood reports from the National Weather Service. And the colors you see are the probabilities. So again, the one-on forecast probabilities compare reasonably well in terms of the aerial coverage of the observed rainfall. And the main thing is the system did predict the precipitation core approximately at the correct location. And of course, there are differences in the detail in the aerial coverage and the amount. Now this is my last example. So this is showing, this is the supercell day on May 1st. We are looking at the 90th percentile of mid-level observed helicity, which is like a proxy for the maximum intensity of mesocyclone. And what you see here is a 6-hour forecast out to 1 UTC. Now I'm going to cycle through a bunch of different forecasts that are valid at 1 UTC. And the star that you see here is the location of Tescott, Kansas. As I mentioned earlier, we are building something in the scale of typical watch to warning. So this kind of this is a kind of build on that principle. So, and the red outline that you see here is a a typical NOAA Storm Prediction Center watch box. And the timing here, this is a pre-convective initiation. So basically, the forecast largely inherited from its initial and boundary conditions from the HIWeather, from which we initialize our one-on forecast system. Now, as you go from 6-hour to 5-hour forecast, you start to refine your threat area, and you may be maybe focus on central Kansas for the maximum likelihood. This is a post-convective initiation. You are starting to resolve individual storm track. You are now getting information about where the threat is within the regional domain, and you are getting the max value at the end of the forecast. Now this is a 3-hour forecast, and as we continue to assimilate the most recent storm observations, the forecast is refined further. So again, this is a post-convective initiation, and the one-on forecast starts to predict individual storm tracks, as you can see, and the focus on the region in north central Kansas. Now the question that we ask is this accurate? This is a 2.5-hour forecast. You see the strength of the mesocyclone from individual storms. Now the hypothetical bounding boxes that are, that are something between, that you see here, the red line, these are something between the watch and warning scale. So basically we are slowly moving from the watch to warning temporal and spatial scales. Now this is a 2-hour forecast. So one-on forecast continuing to hone in on the north central Kansas. Individual storm paths are predicted, and the scale of, as you can see, the scale of the tornado threat is reduced from watch scale to multi-county scale. And this is a 1.5-hour forecast. Move on to the next. So this is a 1-hour forecast. So you have limited down to maintaining really extreme value of observed helicity. The threat area now is the size of a typical National Weather Service warning area. So through each successive forecast, the one-on forecast system is predicting the location of the significant rotation with approximately a 3-hour lead time. Now, as you can see, this ended up verifying really well. This is about a half-a-mile wide tornado that occurred between and it actually is consistent, and basically the one-on forecast system consistently predicted the location of the tornado, and there is a, the one thing that we observed is that there is a really good run-to-run consistency. So we are working on improving all aspects of the one-on forecast system to increase the forecast accuracy. So some of the important areas that we are working on are the ensemble design, which includes like multi-physics ensemble versus single physics versus stochastic physics perturbations. And we are also increasing the horizontal grid resolution to 1 kilometer. And also, I want to mention that for this type of system to reach its full potential, it requires a more accurate measurement of the storm environment than the current observational network permits. So we are investigating ways to improve our near storm environment in the model initial condition. So we are expanding the one-on forecast system, and we are developing or incorporating the capabilities to assimilate new and emerging observation platforms like the UAS, ARI, Doppler wind lidar, phased array radar observations, and other emerging observations. And also we are testing other data assimilation techniques like the particle filter and hybrid techniques. And this is my last slide. Thank you.
All right. Thank you very much to both Glenn and Nusrat for very nice presentations. So we do have a couple of questions. We have time for one or two. One is related to your last slide, and it's from anonymous, related to observation systems and requirements of the warn and forecast system. So the question is, satellites do not see much through clouds. Are observing systems being envisioned to be included to better analyze mid-tropospheric wind, temperature, and humidity in overcast areas?
So we are assimilating satellite observations.
Right, but they don't. The question is what in going into the future, are there observing systems being envisioned to even get those mid-tropospheric winds and information better? Are you aware of those things?
Yes. So yeah, we are. We have a satellite expert in our team, so he is looking into that, and he is assimilating the wind motion vectors and all the upper level satellite observations from the GOES-R, and he's trying to improve that aspects of the atmosphere in our model. Okay. So we have active research going on in the satellite for assimilating satellite data.
Okay. One last question from Bangladesh. I thought I'd get this in because it came from Bangladesh. Mohan, is that what are the reasons for the underestimation of the extreme wind threat?
Say it again.
What are the reasons for the underestimation of the extreme winds by NWP models in general?
There may be, I can speculate, there may be, various reasons. We really don't know. It can be model bias, it can be the resolution, it can be the, the observations, and we are not there yet.
Okay.
Yeah, it's a challenging, problem.
Okay, thank you. Thank you both, to you and Glenn. Okay, we're going to move on. We've got the last but not least presentation. And it's about fire weather. It's from Mika Peace from the Bureau of Meteorology in Australia. And fire weather is one of the foci of high weather. So over to you, Mika.
Thank you. Good morning, everyone. I'm assuming you can hear me and hopefully see the slides.
Yeah.
So I'm going to talk about the work. Thanks. I'm going to talk about the work today that we've been doing with Access Fire, the coupled fire atmosphere model. And we've been working on this for the past few years in a pretty small project, and it's really been proof of concept. And a lot of the conversations that we're having at the moment are really about where we take this capability moving forwards. So here at the Bureau in Australia, there are really two questions that we look at in fire weather when we're talking to the fire agencies and the emergency services agencies. And the first question is about the fire risk on any given day or in any season, which is really about the planning and preparedness. What's going to happen tomorrow? What's going to happen next month? What's going to happen the next fire season? And then the second question is, once a fire has actually ignited and we've got a fire in the landscape, what direction is it going to spread? How fast is it going to move? And what kind of fire behaviour is it going to exhibit? And we're really interested in this study, in this project, on the second question, which is once we've actually got a fire, what's it going to do? And just get the slides to move. Bear with me a sec. Okay. So what I've got on the screen now is a photograph of a prescribed burn, a fuel reduction burn, which was done at Mount Solitary in New South Wales. And the question really is, can we model the three-dimensional interactions between fire and the atmosphere that you can see in this photograph? Because a fire releases energy, and that energy release actually changes the surrounding atmosphere. So without a fire in the photograph, you're not going to have any cloud there, you're not going to have the smoke, and you're going to have a different wind regime. So you can see at the bottom of the convection column there, you've got convergence from all directions going into the convection column. And without the fire there, you're going to have quite a different wind regime. So the fire has altered the dynamics and the thermodynamics of the surrounding environment. And the question, of course, is how is the new environment with a fire in it different from the unaltered state, and how do the modifications actually change the fire behaviour? So we've been running a coupled fire atmosphere model to look at the fire and atmosphere interactions. There's a number of different coupled fire atmosphere models that are available internationally that are being used mainly in research. And what they've got is an atmospheric component and a fire component. And we use them to investigate the interactions between a fire and the surrounding atmosphere. The model that we're using is Access Fire. Access is Australia's research and operational weather and climate prediction model, and it's being coupled to a fire spread model. And the way that it works, you can see from the schematic down at the bottom, effectively we've got the atmospheric model, so the NWP system, runs a time step. It sends a set of surface parameters, so wind, temperature and relative humidity are the main ones, into the fire spread model, which has got information about the fire fuels, how much fuel load there is on the ground, what kind of vegetation structure it is. The fire spread model runs for a time step. It calculates a heat flux from the amount of fuel that's been burnt in that time step, and it passes that heat flux back to the atmospheric model. Now, once that heat flux goes into the atmospheric model, obviously it changes the surrounding atmosphere, particularly the wind fields, and that's how you get the coupling process that steps forward in time. I won't go into the details of the model structure now, but if you'd like to know more, then there's plenty of information available. So what we've been doing is we've run 2 case studies as part of the, I guess, the proof of concept project. The first one was on the Waroona fire, which burnt south of Perth in Western Australia in January in 2016. There were 166 homes destroyed, 69,000 hectares burnt, and 2 fatalities on the second night of the fire. Importantly, there were 4 periods of extreme fire behaviour during this event. There were 2 pyrocumulonimbus events, so fire-generated thunderstorms over the fire. You can see one of the photographs on the first day on the bottom right there. And there were 2 evening ember showers. And the 2 evening ember showers happened when you'd normally expect fire activity to decrease in the evening. The first night, the town of Waroona was impacted with significant community impacts. And on the second night, the town of Yarloop was impacted, both in the evenings. And importantly, the fire behaviour that occurred didn't really reconcile with the current risk measures. And that's largely because a lot of the time when we're looking at the traditional approaches to predicting fire spread and looking at fire risk, we're looking at the surface parameters, whereas what happened at Waroona was really interactions between the energy released by the fire and the atmosphere above the surface. So on the left-hand side in this plot, I've got the top photograph, or the top image, shows the fire reconstruction that was done from a reconstruction of the fire information, and the lower plot is our simulation. So you can see there's a pretty good match for the reconstruction and the simulations, particularly when we account for the fact that once the fire hit the coastal plain, there was quite a lot of suppression activity that occurred. So this slide shows really one of the key findings from the simulations, and what it really, the key point is that the fire and the atmosphere interactions changed the surface spread of the fire. So what we're looking at here is a vertical cross section through the fire at the time of the ember shower that impacted Waroona on the 6th of January at about 9 o'clock in the evening. So the top plot shows the fire line in the yellow and purple shading. The brown and the green shading shows the topography. So initially the fire was running on higher ground on a scarp, and then it came down to the coastal plain on the western side. The streamlines show the wind modification near the fire front. So you can see that there's a pretty big difference between the plot on the right and the plot on the left in terms of the streamlines. And the yellow lines show the location of the cross-section in the lower plot. So these top plots, the yellow lines, are the cross-sections that we're looking at lower down. Now, importantly, the left column, the slides on the left show the coupled version. So in the left, the fire and the atmosphere are interacting. On the right, there's no interaction between the fire and the surrounding atmosphere. So the atmosphere doesn't know that there's a fire underneath that. In the lower plots, the pink and orange lines on the topography show the heat flux, the blue shading shows the wind speed, and the lines show the wind streamlines. So the important things to note in here is that, particularly focusing on the bottom left plot, when you've got the coupling between the fire and the atmosphere, the wind maximum is closer to the surface. So without the coupling, the wind maximum is 500 metres plus above the surface. When you turn the coupling on, the fire actually brings the wind maximum right down to the surface, and that's what's driving the fire spread. The wind is also stronger when you've got coupling on, and the combination of the winds being closer to the surface and also stronger, which means, of course, that the fire runs faster and hotter when you've got the fire and atmosphere and interactions captured. What we can also see in this plot is waves in the streamlines, and that's consistent with turbulence being present, and that was obviously a mechanism for the ember showers that occurred and impacted the two towns. So there was mass transport of the embers observed, and we're picking up in the coupling process that there's a mechanism for that turbulence occurring. And obviously without the coupling involved, you don't get that process. So the second fire that we've been looking at was the Sir Ivan fire. This was in New South Wales in February in 2017. There were 55,000 hectares burnt, 55 homes lost. And in this period, there were really dry fuels due to severe drought in the lead up. One of the significant things with this fire was that there was a pyro-CB, a fire-generated thunderstorm, which developed on a synoptic northwest to southwest wind shift during the afternoon. And what we're seeing in Australia is an increase, and internationally in fact, is an increased frequency in these pyro-CB events, or these fire-generated thunderstorm events. And in 2017, the Sir Ivan fire was the first time that we did an accurate pyro-CB forecast in Australia. So the first time it was seen was 2003 in the Canberra fires, and by 2017 we had some skill in prediction, and in the last fire season, which I'll talk about a bit more in a minute, we obviously had a lot of practice in pyro-CB forecasting. So Access Fire, the coupled model, you can see on this slide, actually produced a pyro-CB over the Sir Ivan fire on the wind change, which was when it occurred. And the processes and the dynamics of it seem to be a pretty good match for what we have in terms of the observations and the simulations. And what we found was that adjusting the surface fuel loads, which obviously changes the heat release, the more fuel load you've got, the more heat's released, the less fuel load you've got, the less heat is released. It showed that in the simulations, in the model framework, we're actually really close to the threshold for go, no go for pyro-CB development. So the boundary layer settings in the model are around about right for generating deep moist convection over a fire. So there's a huge amount of interest in Australia in deep moist convection over fires. And what Access Fire now gives us is the capability to explore these processes in more detail. But one of the things that we've really recognised, particularly from the last season and some of the fire events that we saw, was that pyro-C is an indicator rather than a precursor to extreme fire behaviour. So if we've got pyro-CB, we've obviously had extreme fire behaviour happening at the surface for some time. So what we can do is use the coupled model to explore the continuum of processes that are occurring. So last season, our fire season 2019-2020, it really was an indicator of the future fire risk in the changing climate. And this isn't just an Australian challenge, it's obviously an international challenge. We're seeing changing fire regimes around the world. And what we're seeing here in particular is an increased demand for accurate and timely fire predictions and fire simulations that can be passed to the community during these events. And in the past few years, I've spent a lot of time talking to various community forums, including on radio and various presentations. And I think one of the things that's really quite noticeable is that the science that we're doing around fire and atmosphere interactions really resonates with all of the community, because people can see the processes occurring when they're looking at the photographs and the imagery in real time. So what I'd like to talk about now is three of the fires that we're going to look at next from last fire season. The first one was the Badger fire in New South Wales. It did an overnight fire run of 36 kilometres with deep flaming, and there were media reports of extreme fire behaviour in the middle of the night, including a vortex with tornado strength winds. Now, fires are meant to lie down overnight, but the black and white photograph, which was taken from an aircraft just before midnight, shows that this fire didn't lie down overnight, and we had extreme fire behaviour through the overnight period. And part of the reason for this was that there was a heat wave for several days. It was a 3 or 4 day heat wave. And you had a really shallow overnight inversion. So on the bottom right here, I've got the trace from the F-160 from Nowra, which is near the coast, the closest station to where the fire was. And what you can see in the plot is that we've got this really, really shallow inversion showing up on the trace. But of course, the fire was releasing a phenomenal amount of energy. So it mixed out the near surface inversion, and the fire was effectively running in a daytime boundary layer in the middle of the night. And what this led to was a significant discrepancy between the official forecasts that had been issued and the observations near the fire site. So there was a more than 10-degree error in temperature. And this isn't because the forecast was wrong, it's because the NWP model was doing what it's meant to do, which is produce an overnight surface inversion and set some decoupling overnight. But the fire's energy is just mixed straight through it. So it really shows why we need to be looking at the interactions between the fire and the atmosphere in the predictions. On the top right, I've got a cross section through New South Wales, or southern New South Wales at the fire. And what you can see in here is that there was a lot of wind above the surface. So about 1,000 metres, about 1 kilometre above the surface, less in some points, you had 40+ knots of wind above the surface. And obviously that was what the fire plume was mixing through in the overnight period and bringing that wind down to the surface. Now, in terms of impacts, there were significant community evacuations in the overnight period, so people were evacuating homes in the dark, and we also had fire crews battling extreme fire behaviour in the dark. So that really highlights the impacts of these sorts of events. One of the other fires that we're going to be looking at is the Kangaroo Island fire, which is just south of where I am now in South Australia. So lightning ignition started a number of fires that burned for several weeks. Over half of the island burnt, and many of you would have seen on the international news that there were significant impacts to the native wildlife and the vegetation on the island. The main fire run was with a synoptic change on the 3rd of January, and a reconstruction that was done of this fire by one of the best fire behaviour analysts in the country. It couldn't reconcile the direction and the speed of the surface fire spread with the surface winds. And the reason for that, of course, is that the fire wasn't just being driven by the surface winds, it was being driven by the winds above the surface, which were quite complex as the synoptic change went through. And you can see from the bottom right plot, which is showing us wind observations from 3 of the sites on the island. You had quite a lot of complexity in the structure and the speed of the surface wind change, which was reflecting, of course, the winds above the surface. So what we're expecting is that when we run the coupled fire model, we'll start to see some of those processes in terms of the mixing down being resolved by the model. One of the other things we want to look at from last season is fire-generated vortices. Now, fire whirls happen all the time on fires, but what we saw last season, not just in Australia, but also in the United States, was several fire-generated vortices or fire whirls or fire tornadoes, where there were tornado strength winds more than 300 kilometres an hour. Now, obviously, these kinds of phenomena are a real hazard to firefighters because, in part, they can actually form and move ahead of the main fire front. So they can track kilometres ahead of the actual main fire front, and they have resulted in fatalities at a number of fires. Some of the ingredients are known. We did a report on one of the incidents here in Australia, and what we've got on the right is a schematic that we've produced for communication to the fire agencies about what some of the ingredients are that contribute to these things forming. So one is an intense fire burning up a lee slope, obviously heavy fuels, a lot of energy release. You can't have too much ambient wind, so there's a sweet spot in the ambient winds. If you've got too much wind, you've got too much shear, so it blows the top off the vortex formation. If you've got the winds that are too light, then you don't have sufficient wind for it to form. Lee slopes are favourable because you've got the low level wind shear, which helps spin up these things. And where you've got embers starting new spot fires, obviously as well, you've got another mechanism for local wind shear. And one of the key things seems to be consistent across a number of events is that when you've got rotation in the main convection column above the fire, then you've got a pre-existing part of vorticity. And also where you've got a really strong updraft, you've got the stretching component for the vortex formation. So what we're hearing from the fire agencies is that because of the impacts of these fire-generated vortices, there's really a need to develop predictive techniques. And what we know is that we can resolve these vortices in LES models, and we can also resolve vortices in access fires. There's the opportunity to do more research in that space. So just in conclusion, there's the links between what we're doing in research and what we're doing in the real world. And I spent most of last season working in the various fire agencies around the country, providing briefings and interpretation. And that really provided insights for me into how we link some of the research into the real time. In meteorology, as operations or doing research, we really use a combination of conceptual models and scientific evidence. So there's this pattern recognition from what we've seen in the past in terms of the conceptual piece, and also what we're seeing in the computational model output. And that really provides us the evidence piece for the communication. But in the fire agencies, they're very process driven, they're very systems driven, and documentation is really important. And particularly in these higher end events, there has to be accountability for the decisions that are made. But overwhelmingly, it's not models that are making decisions, it's people that make decisions, and those decisions have to be evidence-based. And that's where I see there's this huge appetite from the agencies to see models like, or capabilities like Access Fire translate into an operational piece so that can be used for decision support. So I've talked about Access Fire, our coupled fire atmosphere modelling capability, which looks at the fire interactions. The simulations have really helped enhance our scientific understanding of what's happening in the fire and atmosphere interaction processes, and that's in part because it's really difficult to take observations in a fire environment. And there's an increasing need and appetite in our fire agencies and also in the meteorologists for more use of this kind of tool, because we're seeing increased fire impacts in a changing climate. And we need to have the robust and the science-based tools to inform the warning messages, and in particular the community response. Thank you.
Thank you, Mika. Very nice. We have just time for one question about verification performance of the coupled fire weather prediction system. How are you verifying the performance?
Yeah, good question. So far, because it's really been proof of concept, we've only run it on a few cases. So we haven't been doing systematic verification. It's been quite subjective. So what we're doing is matching what we're seeing out in the model with the fire perimeter, and that's tended to vary a little bit depending on what fire model's in there, but we've had really good results with one of the model. So that's sort of the first step. The second thing for me is that I've been working with the coupled fire atmosphere modelling for about 10 years now, and spending a lot of time talking to fire agencies and people who are out on the ground. And again, subjectively, we're seeing really good match between what the results are showing in the model and what people saw on the ground that they couldn't explain or didn't match traditional approaches to fire prediction in real time. So we definitely need to do more formal verification as we progress with the model. That's one of the things that we'd like to do. Obviously, that takes time and resources, but from the information available, we're really seeing very good subjective results in terms of what happened on the fire and what the model's producing.
Right. Very good. It sounds like your involvement with the fire agencies is part of the process of developing trust. And they seem to trust your interpretation. And you're, at this point, you're very key in the process.
Yeah, definitely. And that's one of the things, I mean, here in Australia, we've got a great relationship between the Bureau, the Met Agency and the Fire Agency. So one of the challenges is, you know, obviously we understand a lot of these processes subjectively in terms of how the weather and the fire, in 3 dimensions and in time evolution, is impacting the fire. But we really need to embed what we understand subjectively into quantitative methods that fit into their decision process in order for it to be robust and repeatable moving forwards, and moving away from a person interpretation, which is obviously useful and where we're at the moment, into a repeatable product.
Right, right. Excellent. Very good. Thank you very much, Mika. Thanks. I'd like, okay, given the time, we were only 5 minutes late. We were slow starting a little bit, and we're actually on time. So I would like to thank all the speakers for some very interesting, and they were all excellent presentations. Unless Jenny has something more to add, I would like to thank everybody for participating. I would like to thank the colleague from Bangladesh, who it's 3 a.m. in the morning or something, 4 a.m. in the morning, for participating. So these high weather seminars are very well attended by the globe. So Thank you very much. I think we'll end it at this point. Thank you.